It's really hot in the valley, so I decided to come up to Washington Pass to film the lecture. This is exactly what I had in mind when I started thinking about this project. I just went out for a run up the valley, up in there, came back, filmed the lecture, now I'm gonna go back home. What a day, what a day. Welcome to episode 10 of our series on vertex operator algebras. Today we will be discussing tensor algebras, which are an enormous and very general stage which to discuss other algebraic structures. Let's start with a quick review of induced modules. Do you remember the A module induced by a B module V? There we identified two items by taking the quotient of the product space A times V by the linear span of items related by a B action. That's really the ultimate game to play with tensor algebras, taking quotients. There are so many ideals to quotient by. Let's get started. Given some vector space V, we can take the nth tensor power in a familiar way. We identify the first power of V with itself, and the 0th power with the underlying field. Now let's consider the vector space which is the direct sum of all tensor powers of V. Call this beast T of V. Note that, as a matter of notational convenience, as well as sort of usefulness later on, when we begin playing with the obvious grading structure, we will take all negative tensor powers of a vector space to be trivial vector spaces, at least in this context. Indeed, from this perspective, it's pretty clear that T of V is Z-graded. Also, by restricting to the first tensor power, T of V has a clear canonical inclusion map. A little disclaimer, we have been fast and loose with our use of the word tensor. This is pretty common across the world of applied linear algebra, but since we made a big stink about ring modules and the intricacies of associative algebra tensor products, we should take the time to clarify some things. First, the linear space of products of T of V are those of a vector space. No use of any representation of any algebra has been used here. And second, we're going to turn T of V into an associative algebra using the tensor product as the multiplication. So it's a different structure. A priori, there is no sense in which any sort of algebra action is defined on T of V. The tensor algebra. The vector space T of V can be made into an associative algebra by allowing tensor multiplication to act element-wise. In other words, the tensor multiplication becomes a vector multiplication. Indeed, for V, a vector in the mth tensor power, and W, a vector in the nth tensor power, V times W is then a vector in the m plus nth tensor power. So the tensor product preserves the grading in the natural way. V has a canonical inclusion in T of V, so given any linear map from V to an associative algebra A, there is a unique algebra map from T of V to A. This universal mapping property basically determines the tensor algebra. Incidentally, I swear there's some kind of functor between category theorists and the Buddhist monks of the Zen school. Now, T of V is a kind of model for the maximal associative algebra over V. So you might ask, is there an analog for the maximal commutative algebra? Why, I'm so glad you asked. Let's talk ideals. There's an ideal in T of V, formed basically to identify V times W and W times V. Call this ideal I sub S. The quotient of T of V by I sub S will give us the so-called symmetric algebra. As a quick side note, we could replace that minus sign with a plus sign to get the antisymmetric ideal I sub A, which you could use to form, say, the exterior algebra, if this were a different course. The Clifford algebra can be defined similarly. These constructions are similar in spirit to how we define the A module induced by the B module V. But of course, we're dealing with algebras, not modules, so it makes sense to talk about ideals. So now let's talk about the symmetric algebra. S of V inherits the Z grading from the tensor algebra. And FLM points out that S of V is isomorphic to the algebra of polynomials in basis vectors of V. And this will come in very handy next week when we talk about the Heisenberg algebra. One last comment. If V is U-graded, remember that's supposed to be a fraktur capital A, but for now we'll just call it U. For some abelian group U, then S and T both enjoy an additional grading, a U grading, that is uniquely determined by the U grading of V. Of course, they still have that Z grading natural to the tensor product structure. And that's our show. Next time, we'll be discussing the universal enveloping algebras.